Here we go. Okay, guys. So first of all, thank you for joining this workshop. We're gonna have roughly about 3 hours of workshop that will be divided into some theoretical knowledge, some tools and API, and eventually exercise. Well, let's put it this way. In the teams, we don't have the ability to split you guys into groups, but once we're gonna get to the exercise, you're gonna split the groups. Whoever managed to do the prerequisite and have a working environment can join the others, and we will continue this main track with explaining about the exercise, and I can jump between the rooms and help you guys. Okay, so without further ado, let's get started. And again, feel free to ask me anything you need during this presentation. Don't be shy. Okay, so I assume many of you heard the terms machine learning, and then come across the terms deep learning and artificial intelligence. And first of all, I would like to explain in general what is the combination between them, what is the relationship between them. So the definition for artificial intelligence means that you have a techniques that enable machine to mimic a human behavior. Machine learning is considered a subset of artificial intelligence that use statistical methods to enable machine to improve with exercise. Deep learning is a subset of machine learning, and the difference is that it uses a multi-layer of neural network in order to learn and make intelligence decisions. Okay, so this is the connection between those bizarre buzzword if you haven't heard up until now. So when you're working on machine learning world, there's two things that you must understand. Something that it's called an unsupervised data. And one of the nice examples to understand what is unsupervised data, assuming that someone will give you this image, and from some bizarre reason, you don't understand that this is a soccer game, a soccer team. You don't know who is this tiny player with the beard in your left side. Okay, so you have data, but without any information. Okay, a supervised data, from the other hand, and it not necessarily needs to be an image, but I'm giving you data, but I'm also giving you information about the data. You know that this team is a Barcelona team. You know the player, you know their number. Then you understand that number 10 here is supposed to be the best soccer player in our current ages, unless you are a fan of Cristiano Ronaldo, and you will have to disagree with me. Okay. So when you're working on machine learning, it's all about the data that eventually you will provide to your neural network, and the data needs to be labeled. What does it mean? Over here, for example, I have information about houses, their sizes, the amount of bedrooms, amount of bathrooms, zip code, and basically the amount of prices that they cost. So the input for this data, it's called a feature, and the data that they would like to predict is called, it's the output, and it's the label, okay? So with bringing that information into machine learning, I can say, look, what happened if I have this new data, assuming that I have this house that is quite big with 10 bedrooms, 5 bathrooms, and it's in Beverly Hills. So what will be the price of this house? You know, if you can take a look on the previous history that you already have. Okay, so this is something called label data. If you don't have a label data, hold on a second. Okay, there are people today that is dive deep into the world of machine learning that all their job is to label a data. Okay, is to take this a lot of information of data and to label it, which is supposed to it's a lot of work. Okay. I won't dive into the history, but for those of you that think that deep learning and artificial intelligence is something new, well, guys, it's quite old. Back in the 70s, they already managed to basically solve the XOR problem with only one neuron. Okay, so it's not something new, but it's in the past few years, more data science are involved in this domain and become very, very popular. So now it's a question of if I can tell you to think of a highly complicated nonlinear parallel computing system that has more than 86 billion neuron. It has more than 10K neurons, and it can process 1 trillion processes per second. Who will have a guess of what kind of system am I talking about?
The brain.
Right, it was all right.
Of course.
Okay, yeah, it's the human brain. One thing about the human brain, it's called the 100-step rule. It says that the complicated decisions are arriving very quickly. We are human beings, can make a complex decision within the matter of seconds, of milliseconds. And the reason for that is because it contains 100 neuron steps, and each neuron can take like something like 10 milliseconds. So our brain is quite of a impressive and complex neural network systems. So just give you an example of how a biological neuron is actually look like. Okay, so you have the body cells, and you have the signal fiber that connect to the other. Basically, in the neural world, in the neural brain, each neuron is active or deactive depend on the input that he is actually had. Okay, let's just take this 1 minute to take a look.
What do we know about the inner workings of the human mind? Surely everything that humans do, from designing skyscrapers to composing symphonies, is not the product of simple cellular interactions. And yet it might be. Because everything that humans do, or think, or feel, is a result of these basic units of brain structure, the neurons. The human brain contains more than 100 billion neurons. Just like a single ant could never build an anthill, a single neuron can't think or feel or remember. A neuron's power is a result of its connections to other neurons. Each neuron is connected to as many as 1,000 of its neighbors. These trillions of connections provide the playing field upon which the complex activity of the brain takes place. Each neuron can turn its neighbors on or off depending on the signal it sends. And the resulting stable patterns of neuron firing represents memories, and images, and thoughts. We don't yet understand the relationship between neural activity and mental experience. We don't know what the precise pattern of memory or an image or a thought looks like. We don't yet know how to read the cerebral code of the neurons, but progress is being made. We can now watch exactly how various stimuli and memories cause the firing of hundreds of neurons. Perhaps these techniques will allow us to work our way up from the activity of a few neurons to see the structure that emerges from the whole.
So it was just to illustrate you guys on, amount of neurons that we have in our brain and the connection between the two of them. And I think that what you need to take from this short video is that eventually those kind of connections are quite complicated, but one triggers the another and basically activate them. So let's just explain how a single neuron is actually working from the machine learning perspective. So to any neuron, you can have a lot of inputs connected to it. And basically for every input, for every connection like this, we are providing with a weight, okay? And also a bias, okay, that we can alternate the result. And with the result that we are given from the neuron, we actually pass it through an activation function and then determine if this neuron is activate or not, okay? The simple math behind this is actually in order to determine you have to basically take every input, multiply it by the weight, sum all of this, sum also the bias, and then take everything into the activation function, and here you go, you have a result. Okay, this is how a single neuron is working. And as we said, one neuron like this can solve supervised learning problem, for example, the XOR problem. So what is an activation function? There is many activation function out there. We'll just give two examples for the activation function. The first one is a sigmoid. Okay, a sigmoid is an activation function that if your number is basically negative, the more negative it is, the more closest to 0 it will be, and the more positive it, the more closest to 1 it will be. Another very popular and even more common these days is using the ReLU activation function. That ReLU means if you have a negative number, then you will get 0, and if you have any positive number, you will get the same positive number. So the more higher your X will be, the more active your neuron will be. And any question about this up until now, guys? Okay. So when we're talking about a neural network, eventually you have an input, you have output, and everything in between is called a hidden layer. Over here, we are talking on something that called a fully connected layer. There's many possibilities for this. We won't get into the many of them. From now on, also in the exercise, we will use fully connected layer. Mean for every neuron, you have a relationship to every other neuron in this network. One of the things that is more complicated is to understand is the training process of a neural network. So I will try to first with some kind of pseudo to understand it, then we're going to have a very deep dive example. Assuming that you have this information about diabetes, you have inputs, features, that is the age, the BMI, the glucose number, and whether this person has diabetes or not. If I would like to build a neural network based on that information, because I have 3 inputs, I will have to have 3 neurons. And because I have only 1 output, and 1 output, it's not because it's a 1 column, it's because it's only 0 and 1. If I have, for example, an output combining from digits from 0 to 9, then for every possibilities in the output, I should have a specific neuron. Okay, so over here I have only 1. So I have this information, as we explained before. This information is already labeled. Okay, I know what's supposed to be the output in that case. What I would like to do is to take this information to train my model and basically provide with a prediction. So if I have any new observation based on that information, I will be able to predict the result, okay? But I will train my neural network on this specific data. So how it will go? I would set something that called a loss. I explain later on what it means. And the pseudo means very high level. As long as your output minus your prediction result is greater than the loss, you will set your weights to a random number and also the bias. Okay, you run them. You will get some kind of prediction. Okay, you will get y1 in that example. And then you will see if your output minus your y1 is closest to minimum, and we'll explain later on, then you actually know. So the whole point in machine learning is to build this neural network, to train the model in order to provide the optimal weight and bias. So for every input, I will have similar result to the output that I know on my training data. This is in a very, very, very high level, the theory. Okay. Any question up until now? Because I'm gonna go dive deep to this example.
You were talking about categorical data, which we are classifying to categories. And what about continuous data, which is not discrete?
Okay, so this is if you're talking about a situation when you don't have the label data.
No, I'm talking about a situation when it's not categories like 0 and 1. It's like a number from 0 to 100.
Okay, so for every possibilities you have, you need to specify the amount of outputs. So for example, if you would need to provide a number between 0 to 100, in your output, you will need 100 neurons because, okay, even less. I mean, you have to have the combination of the number 100, okay, digits from 0 to 9, okay? We'll have an example later on in our handwritten exercise, it will be more clear. Okay, let's just dive into this, the example, just to understand. Again, none of us are data scientists. I'm not expecting any of you and not myself to become a data scientist, but just to give you an example of the math behind the scenes. Okay, so assuming how the training process is working, I will get the first input into this neural network, set the input to 50, BMI to 33.6, and glucose to 148. I know that the output's supposed to be 1. I already know that because I have the data. Okay, and as we said, the algorithm starts with just providing random number for the weights. Over here, just a random number for the weight and the weights. Okay, and we will follow the math. Math says that for x1, as we said before, we have to bring the b1 plus the sigma of the I multiplied by the weight, and I get a number, 9084. For this number, I have to provide with an activation function. So assuming that we will use our sigmoid, again, you can choose whatever you want. If I will run sigmoid on that number, I will get a number that is 1. Okay, I will do the same thing for x2. The result also will be 1. And now I'm in this phase that I would like to calculate y1. So y1 is b3. Okay, this is all the math. So y1 is turning out to be 2. Then I active also the activation function, and I get the number of .8807. Okay, so the question is, how good is it? My algorithm and my neural network just provide with a random number of weight, and I get this number. So is that good? Is that good enough for me? Then we are talking about something that called a loss. The loss in a very high level. Okay, it's the difference between what you have in the inputs, your no inputs, and the output that basically your machine learning predict. One of the things to calculate the loss is using mean square error. There are a lot of mathematical way to do it. We just give you one example of how to use mean square error for those of you who know these methods. So if I'll calculate the mean square error between the y predict and the y true, I will get a number, the loss number of .0524. So basically, we would like to have this number, okay, closest to minimum. Okay, can someone think of a way to minimize a function?
Gradient descent.
What?
Something like gradient descent.
Okay, this is for advanced. Let's just start with something. Okay, so for those of you that know basic math, the way to minimum something is actually to calculate the derivative. Okay, if I will take the derivative of the loss with respect to the weight, I will get to the minimum. I will probably find the minimum W that I would need to have. But as you can see, the amount of inputs over here, it's not a linear function. This function is, it's not linear. Okay, so basically one of the challenges is how to find not just a minimum, a local minimum, but is to find the real minimum of this function. Okay, and again, who actually answered this? Who was it?
About the descent?
Yeah.
Hiron.
Okay, this is great. Okay, so yeah, one of the math way to do it is actually working with gradient descent. It's quite complicated to explain it here in this workshop, but I actually provide you with a basic example, okay, of how actually gradient descent is working, again, from the very high level, that assuming that you calculate some kind of minimum, okay, and you want to know, basically you just starting from one point and then taking step by step in order to determine if you're on the real minimum and not just stuck on a local minimum. Okay, so if you will think of this dot over here, if I will have a positive slope, that means that I need to go to the left. Okay, and if I have a negative slope, I need to go to the right until I will find a minimum. But the point is, again, it might be a local minimum. So gradient descent, you can think of like you are throttling balls from a lot of places until you actually reach the real minimum, okay? Again, you don't have to understand the math over here, just the general concept, okay? Those step size that each time that I'm starting from one point and then move forward in machine learning, it's something that called a learning rate, and you will see it later on in your exercise, okay? So you can think of that after you have, basically you can calculate the derivative respect to the weight, you will multiply it with something that's called the learning rate, which is actually your step, and then you will have a new W tag. Then the algorithm will decrease the W tag from the original weight that he has, and then you have a new weight. You will have a new. You'll take again the input, and then you will see if you are more close to the minimum. Okay. When we see in the exercise later on, you can set your learning rate between 0.1 to 0.001. How would actually it will affect your training process? Can someone guess?
The more when LR learning rank is closer to 0.01, it will take more time. It will take less time, sorry, because there will be less points that you need to, less areas that you need to go work for. The smaller the sections, the more time it will take you to, and you'll need more samples.
Yeah, again, yeah, definitely right. And one way to illustrate this, if you have a learning rate of 0.1, basically your step is much, it's much aggressive, and you can actually pass your real minimum. Okay, and if you set the learning rate to very low number, your training process can take much longer. Okay, but there is some thumb rules about this number. You will play with this. I urge you to play with this down the road in the exercise and to see actually it affect your training process. Okay, great. So up until now we talk about the building blocks.
Can you go back? I have a question.
Yes.
In the example that you were giving, there are two functions, fx1, fx2, basically like two neurons, right?
Mm-hmm.
Why did you choose just two neurons? Why not 5 or 6? Why isn't it a parameter of the number of inputs that you have?
So you're talking about how amount of input layers of the hidden layer I need to set. Again, over here I just give you an example of 2 because I give you all the calculation for more than 2 is just complicated. Again, you will play with this in your exercise. You will have fully control of the amount of input layers that you have. I mean, in the hidden layer, your input and output, you cannot play with it, right? It's depend on the exercise that you have, okay? But what happened in between, it's only, up to you. And we will see a technique later on that says, one thing that you need to be careful in machine learning is something that's called overfitting. For sure, I can give you the best result I have for the inputs that you will provide me, but then the neural network that you will build will be overfitting, which means that it only will fit to the input that you will provide her. But the challenge here is actually to build something that if you have a new input that you haven't seen, it will be closest to what actually it needs to predict. Okay, so if how
you decide the weights of each neuron?
No, the weight is being okay. So there is something we will see later on that is called TensorFlow that you actually can manipulate it with the weights. But in our exercise, the algorithm is choose randomly. At first, random amount of weight, you will get a score, and then he will alternate this accordingly. Okay. We can see it later on in the exercise, okay? But just remember, it's starting from a random number of weights. He get the result, he compare it to the inputs, and then understand how close it is to this point, okay? This is in general how it's working. Okay?
Again, I think Yossi asked it, but how do you choose the function?
The activation function?
Yes.
Activation function, look, a lot of things in machine learning, and again, I'm not a data scientist, but it's a lot of trial and errors. Some of the things today are considered more like best practices. For example, in the previous, a lot of people use sigmoid, but then realize that ReLU give you better results. So there are a lot of mathematical articles you can read about this, and basically the activation function is supposed to be chosen more to the problem that actually you need to solve, okay? But again, we will play with this. You can play with sigmoid, you can play with ReLU. There's a lot of more examples in the internet, but it's a lot of trial and error, okay?
Okay.
Okay, so one of the things that basically in this example we saw is most of the time when you're working in machine learning domain and artificial intelligence, your data, it's not prepared enough for you, okay? So in Python, there are two Strong's library, what it called a scikit-learn, and the other ones is Panda that we will use in order to manipulate and prepare the data. And if you will take our example for the diabetes example, and basically this example we will meet again in the exercise. Over here, I give you information from the India databases on diabetes. So it combines with a lot of input parameters, frequency, glucose, blood pressure, skin thickness, insulin, BMI, whatever. And just if that person suffers from diabetes or do not suffer from diabetes. Again, it doesn't mean that if you have all of this, you will have diabetes, but it's just like plain data on a lot of people from India, their input numbers, input status, and do they have diabetes or not. If you will take this information like a plain data into machine learning, it will not work. You will need to do some preparation, okay? One of the things that machine learning is not working fine if you have a correlated feature. If you have two features that is correlated with each other, it may cause you some problem in machine learning, okay? And it's the best practice is to remove one of the correlated feature, okay? One of the way to do it is to visualize the data, because if I give you this example and I will ask you to, because someone can think of two things that is correlated with each other just from taking a look on the information.
Skin thickness and BMI. Because
okay.
Probably the more you weigh, probably your skin is thicker.
Okay, great. Let's just take a look, okay?
And also, by the way, people with having zero blood pressure probably don't have diabetes.
Okay, so the point is just to see from the mathematical perspective if I have two features that is correlated with each other. So also in the exercise you have this this example. You don't have to write it down again. Already prepared for you. If you would use the pandas that can do manipulation, and you would use the pay plots, if you will read the CSV, that specific CSV, and you will write down this piece of code, it can illustrate you, okay, with that kind of map. And let's see what does it show to us, okay? This map basically takes each column and correlate him with any other column. So it's obviously, if I will take pregnancy with pregnancy, it will be highly correlated because every feature with himself is correlated. But what can I see here? That's something that called skin thickness and skin, from some reason, are correlated with each other, okay? And this is just a visual way to show me very quickly if I have a correlation between two features, okay? So in order to work fine, I will just go and drop one of them. Randomly, I'll pick skin over skin thickness. You can pick whatever you want, okay? Okay, so after I just I find out that there is no correlated feature or remove the correlated feature, neural network works only with numbers. And over here, diabetes is have true or false, and I cannot work with true or false. I have to convert it into numbers, okay?
Can I ask a question or at the end?
Sure, if you go ahead, yeah.
Okay, so I think about the correlation, it can be that if you don't have enough data, there can be false correlation between things that are not really correlated, isn't it?
So assuming that, again, so you have a lot of information, data that you are work with, and you cannot find correlation.
No, I'm just saying that the correlation can be false alarm. It can't be a real correlation if you don't have enough data.
one of the basic things in machine learning, you will need data, a lot of data. Okay, if you would like to learn from 2 examples, it's irrelevant. Okay, you need a lot of information in order to learn from, unless you are working in a supervised world and you actually building it from while you are going. But this is a completely different thing, and it's out of scope of this exercise. Someone is. Yeah, please mute yourself unless you actually have something that you need to ask. Okay, so one easy way to convert numbers in Python, it's actually build a simple map that says if I see true, I will convert it into 1, and if I will see false, I'll convert it into 0. Okay, and then I'm going to the diabetes column and actually changing the map, okay, to 0 and 1, and now I have numbers in my data. But this is not enough. So I find correlated feature working with only numbers. Machine learning works best when the data is normalized between 0 and 1. I won't get into the math of why, but again, just think of the concept of a neuron that needs to be active or not. You do not want to have a situation, if I have a very high X, then it's active. You want to say if it's 1, it's active. If it's 0, it's not active. It's more simple to understand, more simple to process it. Best practices, normalize your data between 0 to 1. How we can normalize the data? Again, everything I'm showing you is in Python. This is why Python considered a very strong language for machine learning. Okay, if you would use the scikit-learn processing, one of the things that's called min-max scalar. Okay, I won't get into the math of how actually it's working. If some of you want to know, I can explain later on. But the min-max scalar, basically what you can set, okay, you said, I want to use a min-max scalar and to between a range between 0 to 1. You can pass here anything you want. You can normalize your data between 0 to 100, between 1 to 20, okay? For each range that you want, over here, I just want to go between 0 to 1, and I have a scalar. Then I will take my information, okay, and I will do something that called fit transform. Okay, as then you can see the fit transform would take all the information multiplied by a very known factor, okay, and then all my information will be transformed, okay, and then it's what best practice is called. Now I have a scaled data, okay. After I have those 3 preparations.
Can I ask a question?
Yes, yes, definitely.
As you said that we need just numbers.
Just say your name, or I know your voice, but someone else is speaking. Yeah, or go ahead.
If I had a variable which is like a blood type, which is not ordered and is not numeric.
If you had what? If you had a what?
A blood type, for example. It is not ordered and it's categorical. How can I transform it into numbers and make the normalize on it?
Okay, so basically, even in blood type, you have I don't know 5 type. I'm not a doctor. I don't know how many. If it's like 4 or 5, something like this, right?
You can put each one of them as a variable of its own. You can have blood type A01, blood type B0.
This is what you normally do. The point is when you actually do the transform, to do it. For example, you said that O type is 0. I don't know. B negative is 1. B positive, whatever, it's 2. Then you have this, and then you will actually correlate this data afterwards. So you have 2 steps. Okay, you will convert it from strings to integers. Okay, fixed integers. Again, like in the map, like we see here, and then you will take this integer and then scale it. Okay, so like 2 processes. Does that answer your question?
But since that it's not ordered, if I have O minus or R plus, it doesn't mean that one of them is bigger than another. I think we should do.
No, but the point is that if you have 2 types, for each one of them you have a different number. and a constant one. You don't, the order here is irrelevant as long as you said like, O minus is the number 100. For every information that I have in my data, if I will see O negative, it will be 100. So you just convert it, and you know that it's in the feature column that says blood type, 100 mean O. This is how you actually will reverse your information backwards.
But Oran, then it could not influence other categories, like if you give a really, if you give a really meaningful number to blood type, then it can make other categories more.
You can work with this. You can work with this. If you will find, from a very bizarre reason, the amount of integers that you will set to the blood type, then will cause correlation to other numerical column. Just pick other numbers. Okay, it's up to you.
But this is what I meant. If you choose random numbers that with the high range of difference, it can influence the output. Sorry. Not
necessarily. If you will have a constant number for each, for example, take here the diabetes. It's like true or false. We just said that true is 1 and false is 0. We can easily say that true is 10. Okay, and 0 is other numbers. Okay, so for that specific with with the colors, you can check online. There's a lot of, for example, best practices of if you want to predict the color. Okay, like blue. They're also doing this trick with the map, with the constant, and then with the scaling. Okay.
Okay.
Yeah.
I have another question. It's on rate. Maybe you mentioned it and I missed it. Why do we need to normalize the data?
This is one of the best practices in machine learning. And again, I won't get into the math, but assuming that eventually you need to know if the neuron is active or not, it's more easy to understand if the neuron is active, meaning that he's getting to a 1. And if it's not active, he's going to a 0. Okay. It's better to work this way. This is one of the things that's what I'm saying. There's a lot of best practices out there in the data science world, and normalize your data between 0 and 1. This is one of the best practices. Okay.
It's Pablo. Other question. Sorry. If you normalized your training data from 0 to 1, how you will be normalizing your actual data when you will be using this natural network in the future?
That is a great question, and we will see an example in the next slide. Okay, so after we actually scaled.
Sorry, Ron.
Yeah.
When you are normalizing, what you are taking for the maximum? Shouldn't we see the 1 among those input data?
Over here we didn't see the 1. Okay, but again, the real example contained more than 6,000 of entries. Over here, I just take like.
Okay, 10%. So it's just a subset of entries.
Yeah, it's just a subset. Okay. Okay, so after we actually, what I would like to understand is the steps. Okay, the steps is what important. Okay, because it's really the same steps in every almost problem that you would like to solve. After you scale your data, then you need to separate between the features and the column that you would like to predict. Okay, so over here, I'll take all the features, and it says everyone knows that X is supposed to be the features, okay, and Y is supposed to be what you would like to predict. Okay, so right now when I do that, I have my X data and my Y data, the one that I would like to predict. The next phase. Next phase basically will be is to use something that's called train test split. In the test split, what you will need to do is it's taking your X and Y and then split your data into training and testing. Okay, the testing size is 0.2, meaning that I will take 80% of my inputs for training and I will use the 20%. I would not run them under my artificial intelligence because I would like to train my data. Okay, and a random state, you just can have a number between 0 to 1. I won't get into the math because we are basically do not have much time for this. Okay, so after I run the test split data, I will have 4 outputs from this. My X train, okay, my Y train. This is what this is the information that I would use to train my data, my machine learning. And then I will have the X test and the Y test that I will save later on in order to see how accuracy my model is. Okay, and again, sorry for going fast over here because we already passed 35 minutes. 2 important tools to understand, it's what is called Keras and TensorFlow. Okay, so Keras is a high-level framework building up top of TensorFlow. Okay, it contains many of best practices and default values built in that you don't have to actually go specify. A lot of data science like to work actually with TensorFlow. You can see that TensorFlow is the more lower level, okay, and Keras it's like a higher framework building on top of that. For us that we are not data scientists, it's more easy to work in with Keras and not TensorFlow. In TensorFlow, you can actually manipulate the weight and the bias and everything like this. 2 framework underneath the hood. It's TensorFlow written by Google and Theana written by the University of Montreal. Okay, Keras can work on top of 2 of them. We will use to work with TensorFlow. Okay, so after we actually basically we prepare the data. Now we are ready to actually create our model. So then you will need to import Keras, import what it's called sequential model and all the layer. The first phase is actually to build your sequential model. And for every model, you will need to add a layer. The first thing that actually we will add, it's a dense layer. Dense layer, basically, you have an input, for example, a dense layer, and the first parameter is the hidden layer. It's 5. If this is the first layer, you will have to specify the amount of inputs. For example, over here, it's 3. It's dense layer means that it's fully connected layer. There's many other layer out there. Don't mix yourself right now. Use dense layer. It's the more easy way to work with. And for example, for this specific layer, I would use the activation function that call ReLU. Okay, and this is the way that actually you can create more and more and more layers as much as you want. And if you are hitting your last layer, okay, you will specify it over here, said it's your last one, and that's it. This is how basically I build a neural network, okay, with only 1 hidden layer containing 3 inputs, 2 outputs, and 5 neurons within between, okay? And just example, in the last one, I just use sigmoid. Again, you can use whatever you want, okay? After creating the layer, and again, over here, it's also the summary of all the steps that we have taken up until now. Then I'll need to compile my model. In the compilation, there are some of the inputs that we already met. One of them, it's called the optimizer. Optimizer, basically, it's Adam, it's some kind of gradient descent, okay? And over here, I specify learning rate to 0.001. Again, you can choose whatever you want. I also specify that the loss function, basically, we will use the mean square error. And over here, we just something that's called metrics that you provide me with the accuracy of my model. So just you can see over here in the compile, everything that we learn about the theoretical part is also, you can see it in the code. Okay, so it's not disconnected from each other. Okay, here's the learning rate, mean square error that we already discussed. After you compile your model, you will need then to fit your model. Fit in the model, it's actually the part when you take in your neural network and start to actually the training process. So the fitting, you actually provided with the X train, with the information for the training, the Y. You also specify the amount, it's called epochs. Epochs is how amount of time I will take my inputs, all of my inputs, and I will run them through all my neural network, okay? If you will set epoch of 1, you will just take, for example, in our example, it's just 6,000 records, pass them 1, have waited for them, and again, 1 epoch is not enough. You have to run your data over and over again in order to, working with the steps and optimize the weight. Another thing that you have over here, it's something that called batch size.
Sorry, Oron, so what is the learning rate if I have the epoch?
Yeah,
what is the difference?
No, epochs is learning rate is for each one, okay?
For each one, you try to find the mean, and epoch is, then why again do I need the epoch?
The epochs, when you do it again, in the second one, it will choose a different random of initial state of the weight, okay? Then he will actually says, look what I have done in my first step, whether it actually bring me, and then it will take the second one and the third one, combine them all and come up with the best way that he can think of, okay? Another thing in the fit, and please play with this later on and see how it affects, it's the batch size. The more largest batch that I will provide to my algorithm, the faster he will take, okay? That means that I will take in, for example, if you have like 100 records, you take 10 records at once and pass them through and not one by one. Also, again, it's just like trial and error. Best practice means that if you will not use batch size, you might risk overfitting your model to your data. If you will use higher batch size, it will actually, if you have a strong computer, it will work. If you have a slow computer, it actually can cause you slowness. And I'll also recommend to use the Verbis 2 level, because what it will show you for every epochs, okay, it will show you the result of every run, okay? You can see over here for the first result, how much time it takes, the loss, the accuracy of the model, and etc. Okay, so it's very nice to visualize this. I'm not sure each one of our actually will use that, but if you are on data science and you actually want to visualize the training process, you can use something that's called the TensorFlow board. I have this in my folder you can use, okay? If you will write down your logs when actually your machine learning is writing the log, and you will use this TensorFlow board, okay? You go to this specific place, then you will have this kind of plot that actually you can dive deep to see internally. How does the neural network build? What is the weight? What is the bias? And actually, data science is using those advanced tools in order to actually analyze each run and each result, okay? Again, you don't have to use it. I just want you to know that it's not just like just trial and error. It's trial and error and analyze the data. Data science use that a lot. Okay, so after I fit my model, okay, then I would like to evaluate my model. This is the place when you take your testing data, the data that the model haven't seen up until now, okay, you run it, okay, and then you will get the result, okay, the loss and the accuracy, okay, and then this is how you actually evaluate your model, okay. Other things, okay. So the last thing you need to do is once you have your you compiled your fit, you actually evaluate your model. Now you are ready to actually try to predict something. Okay. One of the most important things if you want to predict on on the model that you've built is to use the exact amount of inputs and features in the same order and the same names. So over here, I take the examples, okay, without the diabetes, all the inputs, okay, but the problem is that the data that I will use here, it's not scaled. Over here, in order to scale it to the same information as before, then I will use my same scalar, and I will not use fit transform, I just use transform. Okay, it would scale my data in the same scaling factors as the training one. Okay, and then I would just press model.predict, give him this information and get a result. Okay, I don't know who asked this before, but over here I will get the result of 0.37111. Okay, if I want to do the reverse scalar and feed this to 0 and 1, I will just use something that called predict class. He will take this number and actually will say if it's a 0 or 1. In that specific case, we're going to have a 0. So for example, if you will alternate this information of a patient to my model, it will say this person is less likely to have diabetes. And in your exercise, you will play with this input and see actually how it's working. Okay. One more important thing is that the state training process can take you a lot of time. Once you finish with the model and you think that it's ready, just press save. It will save the weight and the connections between all the neuron, okay? And later on, you can just load it, and it will take you like milliseconds in order to predict something, okay? So you don't have to actually go through all the process just to provide with the prediction, okay? So save and load model is something very common. This is basically what data science is working. If you have a system, they work a lot of times, provide them with a model, then they upload the model to the system, and then we are engineers working with this model.
The presentation will be also in the folder, in the link of the folder you attach?
No, I can send this to you later on.
Okay.
Okay, one last thing before we will dive into exercise and give us a short break. Over here, I just have information like 600 records, but in the real world, you would like to have more data, right? You would always want to have more data on top of your model and to train it over and over again with new data. So how actually you are doing this? You don't have to build it from scratch all the time. Remember, if you have a saved model, you can load it again. And then if you will just take your model and press the fit again with new data of X and new data of Y, again, amount of epochs, he will train your data with this additional data. He would not just destroy your previous data. He will take it as a cumulative number and actually provide it with more accuracy. So this is what it's called like ongoing training. It's been used a lot. Okay, guys, we just now it's hour is 2 and we finish our first round. Any question up until now before I will explain more about the exercise?
Yeah, Maxim speaking.
Yeah.
Regarding to the data normalizing, actually, I just want to understand